absolutely loved this problem from Stanford Maths tournament. So this problem basically gives us a function which is defined as x cubed e to the power x square by 1 minus x square. We have to find the seventh derivative of this function evaluated at 0. Yeah, and this is the answer over here. But how do we begin solving this problem? Like, do we actually take the derivatives? Okay, let's see how complicated it becomes if you want to take the derivative. So we have the function as x cubed e to the power x square and then 1 by 1 minus x square. Now we know that if we want to differentiate, let's say function a, b and c, we know that product rule gives us a dash b c plus a b dash c plus a b c dash. If we use that, this will become 3x square e to the power x square by 1 minus x square, and then the derivative of the e to the power x square will be e to the power x squared at 2x 1 by 1 minus x square, and then this is just the first derivative, and then x cubed e to the power x square by minus 1 by 1 minus x square whole square dot minus 2x. So you see, it's already pretty long and complicated. Now if you again try to differentiate this, like, this will just like blow up, and that would be an absolute mess. So there must be some alternative ways to solve the problem, and yes, there is. So basically, I think you all know how to like get a Maclaurin expansion of a series, a function into a series. That means the function can be represented as f of 0 plus f dash of 0 by 1 factorial x to the power 1 plus f double dash of 0 by 2 factorial x square plus f third derivative at 0 by 3 factorial x cubed, and so on. And I think you notice that in this series expansion, this also captures the nth derivative of function evaluated at 0. Yeah. So from the series expansion also we might be able to find the nth derivative of function evaluated at 0, and that's a pretty useful stuff for us here. So first of all, what we do is we try to find the series expansion for this function. So we know that the function is basically x cubed, and then the series of e to the power x square will just be 1 plus x square by 1 factorial plus x square whole square by 2 factorial plus x square whole cube by 3 factorial, and so on. Yeah, and now this will be 1 plus, now the series expansion for 1 by 1 minus x square will be 1 plus x square plus x to the power 4 plus x to the power 6, and so on. If we multiply all of this, we'll just basically get the series expansion for this entire function. Yeah, but we don't need all the terms. We just need the term involving x to the power 7 and its coefficient. Yeah, because this captures the f7 of 0 by 7 factorial, which we want. Yeah, for other terms, we don't really need other terms for now for us to find f7 of 0. Now to find this, basically let us see all the ways we can have x to the power 7. So since there's already a x cube from the product, like, we want to generate x to the power 4. Yeah, and the way to generate x to the power 4 is basically if you take 1 from here and x to the power 4 from here, x square from here and x square from here, x to the power 4 from here, and 1 from here. So we basically see that all the ways we get x to the power 7 is 1 plus from here also 1 from here also 1 by 2 to the 1 by 2 factorial. So the coefficient of x to the power 7 is actually this is 2 plus 1 by 2, which is 5 by 2. Yeah. So this basically says that in this expansion we have other terms plus 5 by 2 x to the power 7 and other things. And now we also know that this is just f7 of 0 by 7 factorial. Yeah, this is 5 by 2, so that's why f7 of 0 will be 5 by 2 times 7 factorial. Now let me input this in a calculator, and that will give me 5 by 2 times 7. What's the factorials in this? Okay, I don't see it, so let me do it. 7 into 6 into 5 into 4 into 3 into 2, and we get 12600, and that is the answer. So this was a pretty nice and tricky way to find the nth derivative evaluated at 0, and I did like this approach, and I hope you also like this, and in the future you might need this sometime. Hope it's helpful. Hope you got to learn something new. Thanks for watching, and look forward to seeing you in the upcoming videos too.